Okay. Good day, everybody. I'm Giovanni Copini from the Euro-Mediterranean Center on Climate Change, and I will be the moderator of this workshop. So I'm going to start. We'll take 5 minutes to introduce the workshop, and then I will leave you with the other speakers. So I'm working at CMCC, and I'm leading the program on the Coast as a New Frontier. So I'm dealing with these coastal issues, and I'm contributing to CoastPredict. And today we will go through these three talks of Miguel Lorenz from SOCIB, Rich Signal from Open Science Computing, and Giuseppe La Rocca from AGI Foundation. Here you see the title of the presentation. So we will dig and understand what are in our mind the best practice for ocean on the cloud, and for cloud computing and cloud data sharing, and to access our data. So at the end of the presentation, you can use the Slido questionnaire. So we will pose you some questions through Slido, so you can already check them. And of course, you can always use, please use the Zoom Q&A chat to pose your questions and discuss with the speakers. So what is CoastPredict? CoastPredict is a program of the UN Ocean Decade, and Global Coast is an initiative of CoastPredict, and we want to transform the observing and predicting capacity of the global coastal ocean. Here you see the website where you can find a lot of information. We are a team. This is only the small part of the team. So the board, the representative of IOC, UNESCO, and the secretariat at CMCC. And so the CoastPredict is led by Nadia Villi and Joaquin Tintoré. The objective of our program is to provide decision makers, so practitioners and coastal communities, with the integrated observing and predicting system to identify solutions for managing risk in the short term and planning for the long-term mitigation and adaptation in the context of our future climate and ocean change. So we are one of the three programs of GOOS, and we work together also within GOOS with the Ocean Observing Co-Design and Observing Together. Why? I mean, why did we develop, our community develop CoastPredict? Because we believe there is fragmentation in knowledge and efforts, especially for the coastal ocean. We need to establish the network to share information, knowledge, and efforts, and work together. We recognize that there are gaps in observation, both in situ and satellite, but also data itself from the models, products from the model, and we need to make them accessible, available and accessible, collect them, but also make them accessible and shared in a shared environment. There is also technological gaps. There are technology gaps. We need to develop new models for the coastal and especially the urban environment in the coastal area. We need to develop accessible observing technology, low-cost citizen science, and satellite as well in the coastal area. And we need to make this data available and deliver them as a big source, so as you will imagine, also through the cloud. And we need to build trust in our solution. Our capacity of developing solution is very slow, so managers in local community get disconnected from the solutions because probably often are project-based. So we need to trust to make them more trustable, and also develop them with the private community, so in a public-private partnership. So Global Coast is our framework for implementation of CoastPredict. We want to create a globally replicable solution, standard, and application that enhance coastal resilience for both natural and built environments. How to do that? We will develop together a core cloud infrastructure where all the products from the pilot size that you will see in a while will be ingested. The projects of CoastPredict, the core and the affiliated project in the meanwhile will develop new products and new best practice, and these will be all available in the cloud. And with the private sector, we will develop services which will be available and accessible for the community. And here you see the pillars of this process. Our pilot site are CoastPredict and Global Coast, network. Pilot sites are already 130, and they are very nicely distributed in most of the Global Coast regions, and we have already engaged more than 66 countries and more than 350 partners. We have also already identified, with this community, has already identified what we call the impact areas, so the challenges and the most relevant, as said by the community, are the first two: the disaster risk reduction, real-time forecasting of extreme events, and the impact of climate change on the coastal area. But the others are also very well represented. So I thank you for your attention to this introduction. Here you see, so you don't see very well, but we will post them in the chat, our email, and you can contact, you can visit also CoastPredict website. So let's go, let's enter. So I leave the floor now to Miguel from SOSIB to present how to enhance global coast site activities through the integration of tools and with AGI. So please, Miguel, the floor is yours.
Thank you very much, Giovanni. I'm going to share the screen. Okay, can you see the presentation now? Excellent.
Yes, please.
Well, as Giovanni, thank you for the good explanation about CoastPredict, because it's going to be very helpful in my presentation. In fact, to respond to the challenges that you were explaining during your presentation about fragmentation, technical gaps, we are leveraging some technologies that we're exploring in the context of OSTRES project. It's a European project where Oana and Nikos are exploring machine actionable data management plans and science knowledge graphs. And the idea is to see if we can use this in the EG infrastructure. And Giuseppe will be explaining more about this infrastructure, I guess, and see how we can provide support to the different sites. So in my presentation, I will briefly, because you already did a very good presentation about the global cost and CoastPredict, I will explain the diversity of these and the barriers in the second point, and then I will explain a little bit more about the pilot that we are developing under OSTRES for SOSIP, but with the view of expanding this to multi-platform in a more global context. For Jericho, for example, CoastPredict, but also for Embry, we are developing standards that will be useful for a large community. And at last, I will explain how we can use this in the context of CoastPredict. As you really mentioned, is CoastPredict puts the focus on scientific explanation and prediction for coastal resilience around the globe. And by collecting the information about the different sites, we realize that there is a large diversity of things, but there is a large diversity of countries and regions, but also on the institutions, which mean different ways to work, but also on the groups that are involved, the stakeholder groups and the impact areas that you also explained in your brief presentation, and the barriers that we encounter that are of different kinds, but that we can separate into. I separated it for the purpose of this presentation in two areas. One is the technological one, and the other is like the logistic, let's say, with how we get the funding, how these are used, and how we can impact with the activities that are performed here. And I included a few. I mean, there's not a complete list of the possible solutions here on the technical side. We don't have to forget there are many infrastructures that are already supporting the activities in the ocean disciplines, and we had to take advantage as much as possible of those. But the problem is that there are probably too many, and what we are not expecting from the groups on the right side is that they will go to the different data portals and try to investigate if the activities of a specific sites are producing the data that are expected or the results that are expected. So we need something to facilitate this discoverability and to facilitate the work of this um, uh, funding um, organizations, also all the society on finding if we are providing real value with our activities. And this is where our pilot comes into play. We are working, as I said, we are focusing very much on gliders, but with the view we are interacting with other groups to try to find standards that are more complete and can support other platforms. But also we are interacting with people from the EMRI community, not only on the oceanography, but also, for example, with EPOS. And with this example, this particular example of SOSIP, we produce data. This is kind of the data flow, how it goes to the data center, and we have a repository of information where we describe all the metadata related to this deployment, and this can be mixed with the operational information, and everything goes to different data servers. We have a threads server, we have APIs, we have a data catalog. And in the context of this project, we also will include an AirDAP server because this kind of the trend, and this allowed to have federated repositories. And in this particular case, this will be taken advantage by EmonNet and other aggregators in the European community. And of course, with this information, we can make publications and everything. All these resources are kind of disconnected at the moment, but by creating a science knowledge graph, you can define if the publications are related to a specific data set and do some assessments on the impact of the specific data sets or platforms, or even the impact of people and organizations at the global level. And to this is something that we are really exploring in the context of Jericho Core. We are trying to make this science knowledge graph interoperable with other disciplines, stress from astronomy to humanity. This is in the context of EOSC, and EOSC try to facilitate things in a more general context. And in this project, we are also trying to create machine actionable data management plans with our automatic data management plans that can be read by a machine. And this will describe not only the data flow that you see here, and we currently have a description in a PDF format, which is useful for people, but it has its limitation with this machine actionable data management plan. You will be also able to monitor what happened at the different stages of the data flow. And with this combination of science and knowledge graph and machine actionable data management plans, we will create tools that can be used by funders and glider operators to see the status of the activities and the impact of the activities. And this can be pushed to a more general infrastructure such as ODIS, which is ocean infrastructure for collecting. It's like a science knowledge graph at the global level for oceanography, but also can be provided to EOSC or other platforms such as Blue Cloud to to expand this to other organizations, so they will be able to assess their own activities. And that's what I propose at an even more global level, is to each global site can be considered like such a kind of a SOSIP, where they will produce data. I mean, of course, we don't expect that they have the same infrastructure. They will have different maturity levels of their activities. But what happens is that they will produce resources, they will produce data sets, and this can be incorporated into a common, a centralized science knowledge graph. I know this is doing a very good work with this, so the recommendation would be to use this infrastructure that is already operational. And not only this, they will provide this information to the science knowledge graph, but they will take advantage of this information to perform their own activities. So they will be able to find data sets that are in the region or different publications that are related to their own activities through this, all in a single, in a centralized hub. And overall, they will be able to use the tools that we will be developing for CoastPredict for assessments to see how their activities are working, but also funders will be able to take advantage of these assessment tools to see if their activities are worth the investment, let's say. And this is quite important because many times we perform things that are kind of invisible. It's not only about publishing, but there are other things like deploying platforms that create data that are useful for publications, but also for reports, for climate change, and many others. And these central points with SKG can be also for a way to disseminate and to discover information and data sets among global data portals. But before we do that, it's important to notice that we had to define a few things, and this can be done with best practices. That's why it's important to the Ocean Best Practice system, so we can incorporate this best practice there and have a common reference on how the data and information will flow from the sites to the central EGI infrastructure. What are the type of assessments that are worth for different stakeholders? And this can be done for funders, but also for ourselves, for CoastPredict, how we're going to maintain track of the activities and the goals, and if we are reaching the objectives that we have in mind, and also on standards and technologies that will be used to manage and disseminate the data that we create in the project. So to finalize this, so it's I have to say that it's difficult to track data, to track information, but it's very important for ourselves, for funders, and it's important also to discover data and different resources, and also to optimize the work. We are designing a prototype in SOSIP to do this at a small scale, and there is a possibility for expansion if we create the right best practices for the different use cases that we are considering in the project. Thank you very much.
Thank you, Miguel. It was a very clear way forward to manage the data and the observation, and I think it's a very nice experience to share, a very good best practice. So I thank you. I invite everybody to pose questions to Miguel on the Q&A, and also some of the questions proposed by Miguel are also in the slide. So now I leave the floor to Rich Signal, and please, Rich, share the screen. And you have 20 minutes if you can keep the time.
Yep.
Thank you. We see your terminal.
Yeah, I just need to move the.
Yeah.
How do you make the controls small? Okay, I'm just going to move it for now, I guess. Okay.
We don't see the presentation. Oh, now yes. Please.
So, actually, Just trying to get the controls out of the way. How do you get the zoom controls out of the way?
You can minimize or move them.
Yeah. Oh, there we go. Okay.
Did you manage?
I just need to minimize. How do you minimize? It's taking up a lot of space.
Yeah, you can use the small symbol.
Yeah.
Well, minimize the icon. To me, it worked. You mean the bottom one? You cannot
No, I
touch
mean
it.
the top one. Never mind. Okay, I'll try it this way. Anyway, thanks for including me here. We just heard about the overall system and the observational data. I was happy to hear that ERDAP is going to be part of it. I think it's a great, service for observational data. And so I'm going to talk a little bit about how we would handle, or a good way, I think, to handle large amounts of numerical model output. And this is something that this Pangeo community has been working on for about 5 years now. So the title is A Community Platform for Open, Reproducible, and Scalable Geoscience, which is true, but we're really going to focus particularly on model output. So like climate model output, forecast model output, things like that today. And I'm giving this talk, but I'm really kind of representing a much larger community, this Pangeo community. I've worked mostly with the Pangeo community in the US, but there's also the Pangeo community in Europe and Australia. It's really, there's nothing regional about the best practices and the best and the tools that we're suggesting to use for this. So the basic idea is to use Python and use open source tools. And we typically have some packages that form like the core of this system. And one of them is Xarray, which represents the netCDF data model, and some other packages that help us with CF conventions. So those are the sort of standards that we're looking at when we're looking at model output. We're thinking about netCDF files or netCDF data model with CF conventions. And Xarray handles that pack very nicely. And behind the scenes in Xarray, underneath the hood, you might say, is a package called Dask, which automatically parallelizes requests to this Xarray package. So if you, for instance, want to load a bunch of data, and the data is sitting in chunks, some kind of like netCDF4 or GRIB or GeoTIFF, a Dask can read those chunks in parallel using the available processors that you have. So if you're sitting on a particular machine, it can use the CPUs that you have to read chunks of data in parallel and increase the I/O. If you're running on an HPC system, you can create a Dask cluster with something called Dask Job Queue, where you submit jobs to like your Slurm cluster. If you're running on the cloud, there's various ways of creating a Dask cluster that scales beyond the individual machine to do your work in parallel. So the wonderful thing about this is that once you've created this cluster somehow, which varies depending on if you're on your laptop or HPC or on a particular cloud, then the user just uses Xarray, and they say load some data, do some processing, and everything happens in parallel behind the scenes. So they don't have to learn anything particularly complicated about parallel processing. And this package here called Holoviz is something that allows us to visualize the data interactively. So this all runs here somewhere. So it could be running HPC, running on the cloud, running on a remote machine, or running on your laptop. And the user just interacts through their browser, through the Jupyter, or they can interact directly if they want to submit jobs. There's a lot more information about this, of course, on the Pangeo webpage. And so I think I want to actually just, instead of showing you this video, I'm actually going to show you a live demo because it's more exciting, right? So I'm going to go to, let's see, I'm going to go back. And now I've got my controls in the way again. Let me move these out of here. So hopefully you can see this screen. And this is actually a notebook that I've started up. I'm running this on the Amazon cloud using something called Coiled, which I'll talk about in a minute. But this is just a Jupyter notebook, and I'm going to execute a cell. It's going to import some packages, and one of them is like CF array, which works with the CF conventions, for example. And then we're going to open up a data set here, which is a 1 petabyte data set that is in a catalog. So the user just selects this data set by name from a catalog, and then they can say from this catalog, this data set, convert it to Dask. And once they've done that, then they can start exploring the metadata of this data set. So if we can type the data set name, we can see that there are 112,000 time steps. Okay, there's a bunch of coordinates. There's 188 data variables. Okay, and so we could explore these different, these different variables. If we wanted to explore a particular variable here, we can interactively see how big this variable is. So like this variable is 126 gigabytes. So we can explore the metadata without actually loading any data. This data is all sitting on cloud object storage. Okay, so we haven't really loaded any data. If I want to delete this cell, I can just move on. The total data set size here is 47 terabytes for this particular data. So this is a subset of the original data. But if we want to start exploring data, actually loading data and looking at things, we can pick a particular variable, like here, significant wave height. And we can see that this data is in 24 megabyte chunks. Okay, so it's 126 gigabytes, but it's shaped 168 in time, and then it's subdivided in space. So you can see actually from this little picture, it takes about 8 chunks of data to load a map, and then it takes more chunks to load like a time series. Okay, so this is just showing that we can load data from a particular time step. And because we have CF conventions, we just say t equals, no matter what the name of the variable was. And then we can just visualize the data with like one command from hvplot. So here is the significant wave height extracted from a particular time, and this happens to be Hurricane Sandy. And this plot here is interactive, so it really almost starts to look like a web app. So we can hover and see how big the wave heights were in this region, but we can also go over here and like select a region where there, maybe where we can't see what's going on, and then look and see what's going on in another. Actually, let me turn whoops, let me back out. Let's look right in here. So the data rescales when we move the display to show us the full, actually, I didn't really want to do that. Okay. Let me switch to the pan. Let's pan over on this data. And you can see as we pan, the plot updates and pulls in the full resolution of the model and rescales to this region. So it renders on the back end and then just delivers pixels to the screen, which allows us to explore unlimited size data sets of any kind of resolution. We don't need to, we're just delivering pixels to the browser. Now, here I'm going to extract the data just at one point. Okay, and if I ask for just 1 month of data, I'm going to, from this data set, we've selected a particular latitude and longitude, it's going to extract 744 points. And that actually doesn't take a super long time. So if we just go ahead and load this, we're just using the CPUs on this system, and it loads in just about a second. And then we can plot it up. And again, we have these controls where we can see this 1 year of data of wave heights from a particular location. But if we wanted to actually now load a lot more data, then we can use this Dask cluster. And there's different ways of parallelizing with Dask. And so actually what I'm going to do here is I'm going to use something called Coiled, which is a service that allows you to spin up instances on particular cloud providers in particular regions And you can say how many workers you want. You can say what type of processor you want. Like in this case, I'm saying I want an ARM processor to save energy and cost. And, it spins up a cluster no matter what, so you just have Python running somewhere and you spin up a cluster that's running on some other cloud or in some other region. And then instantly you can just start using this cluster to actually load data in parallel. So if we look at like the dashboard, while we're loading this data, we can see each one of these lines is a worker loading data and then delivering it back to the application. So in just a few seconds there, we were able to extract the entire time series, 11 seconds. And now we're looking at a time series through the entire 12 years of data, hourly data. So, we could go back and we can look here, during 2012 again, we could see this Hurricane Sandy coming in here at this location. And, with this cluster running, we can do things like take the mean over, instead of just extracting a time series, because we've chunked this data to be cloud optimized, and I'll talk about that in a little bit. We can just use the same cluster to extract, in this case, 1 year of data, take the mean, and it took 6 seconds. And so with all those workers working away. And the cool thing here was when we actually looked at the sea level or the wave heights over a year, we noticed that actually the waves are actually increasing in the Gulf Stream here, which is kind of cool. Like normally, you might think that just like waves get bigger offshore, but there's like a local maximum in the Gulf Stream because of the wave current interaction in this model, making the effective wind speed actually greater. So I think I'm going to stop there and just go back to the presentation. So I wanted to say too that cost of doing that simulation was about 4 cents of doing that analysis. Okay, so I showed you just these particular packages, but we have access to the entire Python ecosystem here. So we can use things like machine learning packages like TensorFlow or PyTorch. We could work with large tabular data using things like pandas. There's really, you have the whole world of computation at your disposal here. So I like to say that there really is nothing you can't do with this collection of tools and this sort of approach. And although we talked about multi-dimensional data sets with NetCDF4, you can have NetCDF4, GRIB, HDF5, whatever. We actually have developed a way that you can create references to these data sets. And we used to think that you couldn't access these data sets effectively on the cloud, but we've developed methods where we can create references that point into the data and then access these as these virtual collections of these files just as efficiently as if they were in some other cloud optimized format like XAR. And if we have vector data, there's a cloud optimized way of saving that data in like GeoParquet. If we have point data, there's cloud optimized point cloud data. And of course, for remote sensing data, we often use cloud optimized geotiffs. So if you want to distribute your data and have it be used in this way on the cloud, it's important to pay attention to putting your data in a cloud optimized framework. And, it's also important to put your data in a place where that's on a 100 gigabyte Ethernet connection. So, you don't want your data sitting, of course, somewhere where you have like these big data sets anyway, where you only have like a 1 gigabyte connection. Like this was for the USGS, just to show folks that the USGS, all of the locations in the US are on a 1 gig network, except for our one satellite facility, which was on 10 gig Ethernet. But all the cloud providers are on 100 gigabyte, right? So, and I'm sure EGI is also here in this 100 gigabyte. So you want your data to be sitting somewhere that's on the fast network, and you want your computations to be on the fast network. I think I'm going to, well, okay. This is a publication strategy for large data sets that we developed at USGS, where we actually serve the raw data on tape and we give a Globus endpoint so that people can access the original raw data, including us if something goes wrong with the cloud access. But we just leave this data the way it came out of the model on tape, and you can get it if you want to, but it's very slow, of course, and it's not optimized for cloud use. So we create these high value data sets where we take the original chunking pattern in the file, which is usually like an entire time step and maybe all the vertical layers in the model is in one chunk. And so, each time step would be one of these pancakes, and we transform it into a different chunk shape where it makes it more possible for users to extract time series or to make maps or to extract subsets of data and work with them over time. So this is more friendly to more users. And then we try to distribute those on somewhere where there's no egress fees, either in a public data set program like Planetary Computer or Open Data. I don't know if EGI has such a program, but and if not, we store them on something called Open Storage Network. And this is the cost of a petabyte of data. So for storing for 1 year at just commercial prices, 1 petabyte costs about $200,000 on the big three. And there's egress fees. So if anybody accesses the data from another region, it costs a little bit, but if you access from another cloud or from your HPC center or from like EGI resources, you would be paying, or somebody would be paying to access this data. We don't want that, right? So there's other storage solutions that are better that charge no egress fees. And some of them are commercial, like Cloudflare R2 and Wasabi, and some are like Open Storage Network. It costs much less to store the data, and there's no egress fees, and it's a better match for the kind of large data sets that we typically want to use for the usage patterns that we have. So there's lots of benefits to using this approach. As I sort of mentioned, it's very flexible. So you can really solve almost any problem. It's scalable. You can run it on any architecture, as I mentioned. It's efficient that it's just running. People sometimes think Python is slow, but everything that was slow in Python has been, somebody has figured out how to speed it up. Interactive, but also scriptable. As I showed you, visualizable. You can interactively explore these large data sets. It's future-proof if you take this approach, because there's a large community who will be there with you as you move into the future. You may not be using Python or something in the future, but if you're together working with this community, then you don't have to build everything yourself, and there's a clear way to move forward. Open and cloud-friendly. So these are different ways of running. I just showed you one way using Coiled. There's other ways where you can install your own, like on your own cloud, you can install a Jupyter Hub if it's running with Dask on Kubernetes. And I know that EGI has a way to run these kind of workflows. I know that Tina Odaka has showed me some these workflows running on EGI. Yeah, that's it. I guess we'll wait for questions later.
Yeah, thank you, Richard. It's always impressive, and I think we are really building the right community to develop this global coast cloud together, and I think we have all the elements. But then I will leave now. So thank you, and again Q&A in the Slido. Well, better. Some questions are in the Slido. Please be ready, and then use the Zoom Q&A to pose questions. Then I leave now the floor to the last presentation by Giuseppe La Rocca from AGI Foundation. Please, Giuseppe.
Yes, I'm sharing my screen.
We don't see you. I don't know if it's...
yeah, just a second. I want to first... so now you can see me. Let me...
Yeah. You can put it in present. Yeah, perfect.
Yeah, now, okay.
All perfect.
So, good afternoon, everyone. Thank you, Giovanni, for inviting EGI to contribute in this workshop. My name is Giuseppe La Rocca, so I'm community support team leader at EGI Foundation. And my presentation today is organized into different blocks. So first of all, I will just a brief introduce ourselves. So I will present who we are and what we do. So especially for those that are not very familiar. In the second part of presentation, I will explain or I will report some success stories. So basically, community from marine and aquatic domains supported by GI. So I will show you how this solution, the technical support from EGI, is helping this community to do some research. Okay, so let's start with some introduction. I will be very brief. So the infrastructure, EGI infrastructure, EGI is basically a federation of resource centers that are offering capabilities. With the capabilities, I mean not only computing resources and storage capacity, but also software, sometimes also technical skills, because they are offering technical support for helping community to run scientific workflow on our infrastructure. From a historical point of view, this infrastructure is now operational since 2010. At the beginning, we offered support to the WCG experiment, so these high-energy physics communities that are running this worldwide Large Hadron Collider experiment at CERN. But in the last 14 years or so, what we did is try to promote the uptakes of this infrastructure to reach different scientific communities. So today we are happy to announce that we are supporting more than 250 communities from different scientific domains. We are supporting astronomy, astrophysics, together with the community from life science, but also climate change and also social science and humanities. The status of this infrastructure is composed by two different components, let's say. So on the left side, you see the high throughput computing infrastructure. So this is the initial infrastructure when we started. So we offer this kind of capacity for helping communities to run computational jobs like the ones used, for example, by energy physics community. So grid jobs. So you submit your computational jobs to a queue, and there are different workers where your execution or your computational job can be executed. We support different technology, including ARC-C and HTC Condor now. And what is important is even if most of this capacity are available in Europe, you see here there are some blue dots around the world, because EGI over the year also established some sort of collaboration agreement in the form of a memorandum of understandings with other peer infrastructure. This is why we have now a collaboration agreement with the Compute Canada in the north of US, America, but also with the Open Science Grid and also with Africa and Arabia regions, and also with the Asia Pacific countries. So this was the initial status of the infrastructure when we started in 2010. Then we complemented this infrastructure with additional capacity, in particular the cloud capacity, which by now is for sure the service most requested by our customers. So today we have this federated cloud infrastructure composed by 26 different cloud providers. Also in this case, most of these providers are in Europe, but we also managed to federate the capacity also from South Africa, and also two different cloud sites from China. This infrastructure is now operational since 2013. And all the providers of the federation are based on OpenStack. In the past, we also supported OpenNebula and also Signify. And we provide access using command line tools. So there is a possibility to interact, submit computational jobs using a CLI developed by one of the partners of the federation. But we also offer access using a dashboard and, of course, API. So we support different types of API, including, of course, OpenStack native API, but also libcloud and also Terraform. And this is a very flexible infrastructure because this offers more flexibility, especially to address the community of the user. So this is the reason why this is most requested. This kind of infrastructure is mostly requested by our customers. So when we start in 2010, all the members of the infrastructure share together this vision. So the vision is to allow to have a transparent access to different resources and services, and give the possibility to different researchers to support advanced research and innovation. So in order to achieve this vision, all the members of the federation has a mission. The mission is to deliver open solution to support advanced computing and data analytics. All the federation is coordinated by a foundation. There is a non-for-profit organization based in Amsterdam under the Dutch law. So the responsible of this EGI Foundation is to coordinate and make sure that the infrastructure is operational on behalf of the member states, and also enable international collaboration with the communities. We have a council, which is the board of EGI, where important decisions are discussed and agreed. This is the board where decisions like the vision, technical roadmap, etc., are discussed. This board is currently composed by 29 different partners representing international research organizations and institutional representatives. We distinguish between full participant, the ones that you can see here in blue, and the associate participant, the ones in orange. And this is where EGI Foundation is based. So the offices are based in Amsterdam. I'm officially a member of this foundation teams. Even if I'm not based in Amsterdam, I'm working remotely. So in Amsterdam, there are more or less 15 people, and the majority of the staff is working remotely. What I would like to bring to your attention is that in the Council of EGI, there are two important partners from marine and ocean domains. The first one is EMSO-ERIC, probably you are aware. This is a pan-European research infrastructure for ocean observation, which enable real-time monitoring of different ocean processes. And the second one is MARIS. This is an SME based in Netherlands, which is playing a key role for the developing of technical infrastructure and defining long-term strategy to support the exploitation and access of marine data. So these are two important partners of EGI, and we established this collaboration. We established a collaboration with them since a long time now. So in this slide, I'm going to show you briefly the typical workflow that we adopt in EGI to engage with scientific communities and the research infrastructure. So what we usually do is to organize a sort of technical meeting with the community representative. So the idea of this, the goal of this meeting is just to collect the technical requirement from the community, understand which kind of application pilot they would like to run on EGI. During this meeting, we do not only try to identify the capacity requested, but also identify which services from our portfolio can be adopted or customized to meet the customer expectation. So with all this information, EGI works as a broker. So what we do is to start a sort of a matchmaking process. So we contact our services and the resource provider of the federation and try to understand which of them are best available or suitable to support the community needs. So if this matchmaking process is successful, so this means that we have collected expression of interest from a resource and the service provider. Usually EGI establishes a service level agreement with the customer. Most of the time, this is not a legal binding contract because the cost to access this capacity are paid by the funding project. But if this is not possible, so if, for example, the customer is from outside the federation, let's say, so in this case, we can also consider the possibility to have a pay-per-use model. At the same time, EGI established this operational level agreement with all the service provider, resource provider interested to support the customer. We do so because we want to monitor the service performance. So we want to make sure that the services are delivered to the customer according to the expectation. We also perform this sort of regular monitoring, and we generate service performance report every 6 months. And if there is some problem, there is some violation, we try to understand what's the reasons of the problem and try to identify mitigation plan to solve it. And at least one time per year, we also organize checkpoint meetings with the customers because we want to get feedback from the agreement, understand if there are rooms to extend this agreement, to extend the capacity, or also to collect feedback and suggestion for improvements that can help us to understand how we can evolve our service offering. We have a service portfolio which is published. This is the official website of our service portfolio. Here you can see all the full list of services and solutions that EGI is offering to target the different stakeholders. So far, we have 3 main stakeholders. Of course, the most important stakeholders for us are the scientific research. So provide solution for helping community to do advanced research and innovation. But we are also offering tools and solutions for all the members of the federation. So we are a federation, so the different teams, different capacity, and this solution basically improve the way we work together in a DC federated environment. A couple of years ago, we also established this digital innovation hub, but this is an incubator because we want to engage also with the business sector. So this digital innovation hub gives the possibility to the business sector, SME, startup to do some testing on our infrastructure, for example, before to do the real investment, or also engage with our community and develop together new solutions to improve their visibility, for example, et cetera, et cetera. Okay, this is just an infographic. This is the full list of solutions that we are offering to target the research sector. So I can see there are grouped for by different categories. In the compute categories, we have the cloud, but also the high throughput compute, container, and as I said before, the cloud compute and the container are the most requested from our customer. We have solution to facilitate the orchestration of cluster in our infrastructure. For example, this infrastructure manager is a solution to deploy virtual and elastic cluster on top of cloud providers. This is flexible because there is a possibility to scale up automatically, scale up and down the size of this cluster based on the scientific workflow. Solution for the data management, but also security, because security is usually an hot topic, especially in a GI federation, because we are a federated infrastructure. And we are also offering training, FIDSM training, for example, if you are interested to improve the IT service management system of your company and improve the way your services are operated and delivered to your customer. So this is a very brief introduction about DJI. I will stop here with some statistics from the last annual report. So we are currently supporting more than 95,000 users across the different disciplines, as I mentioned before. This is the total amount of capacity delivered in 2023. And we are particularly active in Horizon Europe project. So we are currently involved in 36 projects. Some of them are coordinated by GI, but the majority are coordinated by other partners, and we are just participating as a beneficiary. And this is also important. This is the number of scientific publications that has been published in 2023, thanks to the support and provided by GI. So I put some reference in some pointers to documentation where you can get additional information, and these are provided in the last slide. But now I would like to move to the second part of the presentation. So I will show you some concrete example of community from this marine and oceanographic domain supported by GI. I will start with the first one from aquatic science domains. So if you are aware, in Europe, they are doing a lot of investment in this scientific area. So more than 1.4 billion euro per year in marine data acquisition is the total budget invested by Europe. support this research. And as you can expect, this a huge amount of investment are generating a tsunami of data that we need to process and analyze in order to extract scientific insight that can help us to improve the knowledge, the understanding of the marine and oceanographic domains. So Imaging is a EGI flagship project, so is one of the projects coordinated by EGI, officially started in September 2022. And the goal of this project is to help the different research infrastructure that you can see here, EMOPNet, CITEDANET, EMSO-ERIC, Copernicus Marine Services, and EUARDO. So the goal is to help this research infrastructure to develop a new solution that can help to improve the processing and analysis of imaging data from marine sector. This goal is achieved by providing access to a portfolio of 3 other point of views image data. We also provide access to a generic AI platform where researchers can train and test their model. And also, of course, we provide technical expertise to do some analysis and processing this image dataset. This is the typical approach that has been implemented during the context of the project. So we started from the bottom. We have an infrastructure layer. We have a different cloud provider of the federation interested to support the project. So they are offering different capacity. You see the total amount of storage, GPU, and the CPU capacity offered. These are the results of the matchmaking process, so that I explained it before. So we have 4 different providers. One is based in Spain, in Portugal, Turkey, and this is from Ireland. On top of this infrastructure, the project deployed this generic AI platform, which is powered by the AI for IOSC. This is another IOSC-related initiative. So we are not reinventing the wheel. Basically, we are reusing a solution that has been developed in the context of other projects. And this platform, AI platform, is currently used by different community, different use case. We have in total 8 different use cases plus additional 3 that are external that has been selected with a dedicated call. And this platform gives the possibility to create, train, and evaluate the models. And the beauty of the project is that once this model has been assessed and evaluated, they are stored in this model repository, which can be shared with other members of community interested to do similar analysis. So this material is shared with others. And also the data set to train the model are usually stored in Zenodo, and all this information are made available to others. Okay, the project is coming to an end next December 2025, but there are still open, it's running open call for AI-powered image analysis. So if you are interested, this is the typical support that you can get from the call. So you can get access to this AI platform from where you can do this analysis, get access to the capacity, GPU, CPU, and storage, and also technical support from the team involved in the project. So if you're interested, you can see here the QR code, so you can scan the QR code and you can submit your application. I can move to the second community I want to present. Okay, these are Aneris is another easy funding project. It's a 3-year project officially started the 1st of January 2023. And the goal of this project is to develop the next generation of scientific instrumentation tools and method for sensing marine life. The mission of the project is to, the project implement this new concept of operational marine biology for a systematic and long-term measurement of marine dataset, and also their rapid interpretation and dissemination. So this concept of operational marine biology is implemented through different steps. First of all, there is the acquisition phase. So all these kind of data set from ocean and coastal life are acquired using different techniques that I'm going to show you briefly in the next slides. There is a validation phase. So as soon as this data is being validated, so there is a sort of quality control. This is created and injected in the infrastructure in order to allow different user community to do some interpretation and disseminate. So the different techniques used to generate this, to acquire this data set are different. We have this genomic sequencing, but also citizen observation. So there are people that can use their camera to collect this information about the coastal, and also underwater observation. So all this kind of information are used by the project to generate these OMB data products. And this is the final goal. So the plan is to contribute to improve the common understanding and the spatial resolution. This is the additional information that the project can provide to the communities. And yeah, the last, yes, this is the contribution of EGI in the project. So we are not leading officially the project, but we are contributing as an infrastructure provider. We have a dedicated budget to offer capacity and also to provide technical support. We are also involved in the innovation, management, exploitation, and also support integration with the other IOSC-related projects. You see here some statistics, and you see the provider of the federation that are supporting this project initiative. And the last example of community that I'm going to present as quickly is Blue Cloud 2026. This is another 3-year project, especially coordinated by the Consiglio Nazionale delle Ricerche in Italy. This is a follow-up of the Blue Cloud project. And the goal of this new project is to deliver fair and open research ecosystem for oceans, sea, coastal, and inland waters. So the project is supposed to develop these 4 different objectives. The first one is the data discovery and access services. It's a sort of catalog of data. So it's a metadata catalog from where you can get access to the different open data sets from marine domains. The second objective is represented by the VIII, the virtual research environments. And this is the place where it is possible to do some data analytics with the data identified before. And the third object is the essential ocean variables. So these are basically curated data for a specific sector, for a specific cities sector. And the last one are these virtual labs. We have 5 different virtual labs. This is the place where it is possible to do some research. There are thematics, so different domains. In each of these virtual labs, it is possible to get access to the essential ocean variables and do some data analytics with the one of the available VIII. By default, the project rely on the default science virtual research infrastructure, but there are also possibilities to use the Jupyter notebooks, for example, etc. So EGI, in the context of this project, is helping with the setting up of these data lakes, so providing expertise on setting up this first objective. We don't have a lot of effort, honestly. We are mostly involved in this second objective, VIII. We are offering EGI notebooks, our Jupyter App technology to combine together, which offer this environment where you can put together code, data set, and perform some data analytics. These notebooks usually offer some capacity. We support different types of kernels, including Python, Octave, R, but also MATLAB, because in the past we established a collaboration with the MathWorks. So if the user has a valid license, it can also launch a MATLAB environment in the context inside the EGI notebooks. And we are also participating in outreach activities. We are primarily responsible to engage with other IOSC-related projects like imaging that I mentioned before. And there are also other. Okay, so this is my final takeaway message. So the infrastructure operated by GI is quite flexible. We are offering a lot of resources and services to support research. And on top of this infrastructure, different communities so far were able to support to deploy their domain-specific platform for serving their community needs. There are solution capabilities like artificial intelligence and machine learning. We have Jupyter Apps and Binder App technology for supporting the reproducibility of open science. And yeah, we are happy basically to engage with the community, in particular also from the marine ecosystem now. As I promised, these are a list of reference, so some pointers from where you can get additional information about the service portfolio, a list of publication. There are also some success stories. Some of the use cases that I present are already available in our website. You can also get this kind of information. And this is the official mail list if you want to get support from us. And this is my last slide. Thank you.
Thank you, Giuseppe. It was a third fantastic presentation, and I have more and more the feeling that we have really found the right community to build our global coast cloud and the right expertise. So we move now to the slide, but before doing that, there is a first question there is a first question. No, there is a question on Slido that Nadia is asking how scalable is the AGI infrastructure for the world. Could it be better to think about a federation system? So maybe you want to answer live.
Yeah, it makes sense. In fact, as I mentioned before briefly, but yeah, probably I was a bit too fast. So yeah, we have this federation in Europe, but AGI in the past also established this collaboration with other infrastructures. So we have also a collaboration agreement with the US, and this gives us the possibility to rely also on the capacity offered by Open Science Grid, for example. So during the COVID time, there was a structural biology community, for example, that they requested to scale up additional capacity. So thanks to this collaboration, we were able to dispatch job across Europe and the US, to do this kind of analysis and collect feedback, result, etc., etc. So similar.
The federation is possible.
Yeah, definitely.
Yeah, and that I think is the way.
This week, there is my colleagues in South Korea, because yes, we are planning to have a collaboration also with this partner. So just to give an idea.
Very interesting. There is another question for you before moving to Slido, and it's Richard in the chat asking if AGI has object storage with the S3 API, right? How much does it cost to store 1 petabyte of data for a year? And are there a grease fee?
Okay, so basically, the federation is composed by different providers, as I mentioned before. We are supporting object storage because based on Swift. This is the official object storage from OpenStack. Some of our providers of the federation are also offering S3 endpoint. So this is also another possibility. We need to consider a case by case, which is the best provider fitting the requirement of the community. This is why the matchmaking process that I mentioned before is important. We need to collect the requirement and identify which member of the federation can offer the best support for the customer. But in principle, yes, S3 API are also available. In terms of the cost, I cannot provide an estimation because each provider has a different cost. Of course, more or less these costs are more or less the same, but yeah, we need to consider also in this case a case-by-case analysis.
Egress fees? What about the egress fees?
Yeah, there is also. Yeah,
there are egress fees.
You said yes, Giuseppe. Sorry.
Yes.
Yeah. Okay. So maybe it's a good. We try to estimate this cost and share this information, even if there is a variety, as you are saying. But I mean, to understand,
Yeah, I
to
can
do
provide,
an
we did
analysis
an
similar to
exercise.
what Rich has done.
Yeah, we did an exercise a couple of months ago, a couple of years ago. We provide a sort of estimation, an average estimation of the cost of to use the cloud capacity, GPU capacity, and also storage. This information I can share with you. It's a bit outdated because it's 2 years old at the moment, but yeah, this is something that I can do.
Okay. There were some questions and already answered, so we can move to slide, and I ask Ariba to help me.
Sure, but Giovanni, there's another question in Q&A for Giuseppe before we move to the Slido.
I can't find it. Sorry, just a moment. Do you want to read it?
Sure. So Jay's asking from Giuseppe is if NRS identifies methods for validation, how are the methods to be documented and where will be available?
Sorry, I cannot see this question in the chat.
You have to go to the open question.
Yeah,
not
it's in the
answer.
Q&A. It's not in the chat, it's in the Q&A.
I don't see Q&A.
Okay, maybe you check for it. I copy in the chat.
Okay,
And
maybe it's
then,
better.
in the meanwhile, we can go to the Slido because otherwise we will be late. You find it in the chat, Giuseppe. You can answer there.
Okay, so for this question, yeah, well, I'm not directly involved in this project, so I can ask my colleagues. Maybe they can provide more information here. But yeah, I'm sorry, I cannot provide you more details for analysis.
Thank you. Okay, please. Ariba, the floor is yours. You want to read the questions? No, it's automatically. I see. So people are.
So if everybody scans the QR code, they will get the questions on their phones. If you want, I can also read the questions.
No, it's okay. It's okay. I mean, it's otherwise it starts to be messy. So now we will wait a moment to get enough answers, and then we will ask the panelists to comment on these results of the. So let's wait a moment more. So we have 15 minutes left. So maybe we want to start discussing the. So can we go to the first pool? Okay, then here we have what are, so now I will ask Miguel, Rich, and Giuseppe to comment, I mean, to freely comment on these results. I mean, if you were expecting them, if it's something new, if it can be improved. I mean, there are different questions, so please comment if you feel you want to add something. So the first one, we have analyzed through the participants, what are the key infrastructure of your region that play a key role in data management and data sharing. So we see a majority of the national data centers, and then progressively academic and research institution, public government portals, and less. And that's the first interesting maybe result. Less the private sector, and also not very well known or used international data networks. Yeah, so maybe it was a bit misleading, the community driven, because I guess it's in the first also, is in yeah. So please, do we want to comment on that? Do you have any comment?
Well, I would say that I'm not surprised at all about this answer collected, because yes, the key role are so the data set are managed usually by a national, regional, institutional, or data provider. So I was expecting to have this kind of feedback from the audience, honestly. And as you said, yeah, there are less engagement with the public sector and also with the external cloud-based platform like AWS and Google Cloud, because probably there are some problems to store data outside, well, at least for Europe. For European research, it's not a good practice to store data outside the European legislation. So, yeah.
And do you think this will be an issue when we look to interoperability, or no?
Well, no, but I know that in some cases, for example, in the health domains, there are some sensitive data that you need to analyze and process. So in this case, you need to make sure that the data is preserved in order to avoid to preserve the confidentiality, etc. So in some cases, it's obligation from the Commission that they say that do not expose your data outside to the countries, the European countries. So,
But there was also an aspect on caching the data, I mean, to allow easier access outside the region, let's say, or on another cloud. So you think this would include some discussion if we cache European data in the Australian Amazon cloud? Do you think we will have to tackle this?
well, the issue I think that was raised by Richard is the connectivity. So if we need to process data across countries, yeah, in continent, we need to make sure that we have enough bandwidth to connect side. But yeah, apart from this, I don't see any big issue.
Okay. Any other comment from Richard, Miguel, or otherwise we move to the next?
Yeah, I think as Giuseppe said, is what was expected, and I think the role of the small research infrastructure is quite important, and we forget sometimes because data is on the big portals that they are the feeders of all this data. So it's important to give them the recognition that they have, and also I would say also some funding to allow them to push this data to the big data portals and to make them to standardize them and to put in place the specific procedures for this to happen.
Thank you.
Yeah, maybe I could just add that it's a little bit ironic that the best place to store the data for cloud-based access right now is not on the major cloud providers because of these egress fees. And really the best place to store the data is like at academic institutions and at HPC centers, again, on object storage on the high-speed internet. And I mean, this is true of model output, right? Like, you know, when you're talking about hundreds of gigabytes, terabytes of data, or, you know, or petabytes of data. But it's something that everyone, I think, is moving toward. A lot of larger institutions, HPC centers, certainly in the US, are moving toward hosting their own data on object storage on a high-speed network, and then building data services on top of that. So you can either go to the data services like, you know, with Threads or OGC services or whatever, but then you can also go directly to the object storage, which of course is more robust and scalable. So I think there's a movement in that direction, but it's by no means very widespread so far.
Thank you. So let's move now to the next question. Yeah. So in which way do you think that CoastPredict could support sites' activities, management of their data? When we say sites, here we mean pilot sites. So the pilot site of Global Coast, management of their data and the assessment of their activity. And here, I guess we have been the community that answered is saying facilitating access to advanced data sharing platform, offering training and capacity building and data management, but also promoting best practice. So basically all of them, improving data interoperability and data integration, and I'd 50% providing standardized data management guidelines, enhancing collaboration through stakeholder networks, and also developing tools for assessing the quality and impacts of the activity. So basically, we have many opportunities to contribute to the local community to make everything more equitable. I would say that's a key, at least in my understanding up to now, since the last 2 years of CoastPredict. So we need to really make accessible and equitable the data access in the solution. But please comment on that if you wish. Yeah, I guess we don't have big surprise.
Yeah, I think that shows that the people what they need is, as I was saying before, they need some guidance to make this to make data available at the large scale, because what they want is to allow to show them how to provide this data by offering training or by offering facilitating access to these platforms. And these platforms can be like Emonnet, but it can be, as Richard was saying, some cloud platforms where you can process and do some more advanced work.
So let's say we can keep these points as our action plan for the next 2 years. While building the cloud, we need to focus on all these very important opportunities and objectives, let's say, of activities. Okay, we can move. We have the last 5 minutes, so we can move to the next. So this is more for Giuseppe. How do you think AGI, but I guess it applies also to Pangeo if you want to comment, but can AGI be the driver of your groundbreaking research? And the most important is providing access to federated infrastructure of resources, cloud services, and related user support and training. And then also providing access and support to cutting-edge technologies such AI, ML, and big data analytics. So do you consider these challenges, Giuseppe, reasonable?
Well, this is more or less the same expectation I receive from other communities. So the first request is, yes, to have this shared access to our infrastructure, use capacity to deploy and then platform or domain-specific thematic services, etc. We are already running training programs. We started during the COVID with webinar programs. In our website, there are, I think I put the link in my presentation. There are links from where you can get access to the webinar organized so far in the last 4 years, 5 years now. And so all this kind of material are available. We can also consider to have something dedicated for the community if necessary.
Thank you. Let's go next. Then, are you currently using the cloud for processing, analyzing, and visualizing big Earth system data? And as a matter of fact, the answer is no. So we have let's say a duty to go ahead and make more accessible even the cloud itself. So not only
Probably because of the need. Yes, we need to provide this sort of training. So
yeah,
explain how exactly how to do this kind of analysis on federated infrastructure like EGI, for example.
And just to mention that we can federate also the training opportunities. And for instance, CoastPredict now is working a lot with the DCC on coastal resilience to really develop this training, and I think we will do it more and more regularly. If connected to the first question, to the second last question is if you are not using the cloud for big Earth system data, why not? And exactly what you were saying, the training is missing, and also the cloud computing is too expensive related to our on-premise computing facilities. So. But first, let's start with the training.
I'm curious about what Giuseppe and Richard thinks. Is really more expensive because there is a cost that is not obvious. Maintaining systems and servers and storage in your organization.
What I meant was, when I created this question, many people tell me that their institution already provides them with on-prem computing, and if they want to use cloud computing, they have to pay out of their projects. So, that's a problem, right? But that may be a big problem depending on what institution you're at, and many institutions provide HPC capabilities for their folks for free, and then I think most assessments would say that if you know how to use the cloud effectively, the cloud will be cheaper. But you have to know how to use the cloud effectively, and that comes back to this training, because the cloud is more complicated, because there's many more options for how to do your workflow. And one of them is going to be the most efficient and effective, but you may not understand that, and you may run some other workflow that costs you more money. So it's, it is more challenging, but it's definitely something that is not only more scalable. You can get your results faster. It's going to be cheaper if you know how to do it, and of course anybody can do it, not just the people with the big computing resources.
So I'd like really to thank the speakers and the attendees to stay with us till the end of the workshop. We are very happy as a CoastPredict community to have organized this. I think it was very successful, and I think we need to keep also this level of a workshop, or the workshop at this level should be repeated maybe in 6 months or 1 year, to be sure to monitor the progress and to offer to the community the information on the progress, because we are already working to develop with this team the new infrastructure that will be available. And so with this, I really thank you all, and hope to see you soon in the next occasion, in the next workshop. Thank you so much to everybody.
Thank you very much.
Thanks, Giovanni.